Hello, ladies and gentlemen, and welcome to Mr. Saucedo's YouTube videos. Today we're going to be talking about rate laws. So a very common kinetics question whenever you're looking at like a kinetics problem is always to find the order of the reaction. So something that we've already talked about, which is equilibrium expressions, often get confused with rate laws, but they are totally different than equilibrium expressions. It's just they share some similarities, and so people often mix them up because they say, okay, I'm going to just quickly try to solve this, and they accidentally use the wrong kind of format. So here's what a rate law looks like. It's the rate is equal to a constant, which we call the rate constant, that's what K stands for, times the concentration of whatever your reactant A is, raised to a power n, times whatever your reactant B is, raised to the power m. So already this kind of looks like an equilibrium expression. But notice there are no products involved. So there's nothing to do with products in this kind of reaction. The other thing to point out is that the order that we're looking at here is additive. So what that means is that whatever n is going to be considered the order of A. So if I have a 1 here, that means I would have a first order reaction in regards to just the reactant A. If I had a 2 where m is, that means that I would have a second order reaction with regards to reactant B. But if I'm looking at the overall rate law, then I would add together n and m in order to get what the overall order of the reaction is. So if n is 1 and m is 2, that means the overall reaction rate would actually be third order, or the third, okay? Now, something else that you need to be aware of that, again, is a problem because equilibrium expressions are often mixed up with rate laws. N and m are determined by an experiment. They are not from the balanced equation. So even if I saw a nice balanced equation for A and B being mixed together to make some product, whatever coefficients I see in front are not related to what N and M are. And even if they are, if for some reason it's like, oh yeah, like, you know, I put a 1 in front of A and it just so happens that it's first order with regards to A, that's purely coincidental. There's nothing to do with the balanced equation in our rate law at all. Now, only the concentrations, like I said, of the reactants matter. So A and B in this situation are reactants, not products. That does mean, because very rarely do we have more than 2 or 3 reactants in a reaction, that for the most part, you'll only see 1 or 2 reactants in a rate law equation ever. You very rarely will you see a third one, but you almost never, I've never seen one that actually has a fourth term in its rate law. So let's start with the simplest one, the zeroth order reaction. So a zeroth order reaction, even though I'm dealing with it first, isn't exactly the simplest, but there are at least some simple examples. So for example, if I have dinitrogen monoxide and I'm breaking that apart into nitrogen and oxygen using a catalyst, this is the kind of data for my experiment that I might find. So if I have a concentration of 0.1 moles per liter for dinitrogen monoxide, then the rate of the reaction would be something maybe like this. If I increase that and instead say, okay, now I have 0.2 moles per liter of this, the rate doesn't change. And then even if I were to double it again and double it again, notice that the rate is pretty much the same. So a zeroth order reaction, what happens when you double the concentration is the rate law does not change at all. So when I'm looking at my rate, I get absolutely nothing changing. If it does change, it changes very little. If you're wondering why, there's a really difficult kind of way of picturing this, but if you have a catalyst, like let's say a piece of platinum or something, right? Only a certain number of these molecules can fit onto the surface of the platinum. And even if I increase the amount, I'm not increasing the amount of platinum, I'm just increasing the amount of this. And so it's not going to occur any faster. It's just going to occur at the same rate it was already. Now, this rate law does expire, which means that eventually the rate will, when you're looking at it, will eventually hit 0. And you can't technically have like a negative rate. You can't like all of a sudden go into the negatives. So that does mean that this is normally a starting place for a reaction. and then afterwards the mechanism changes somehow. So the K though, if I wanted to know, hey, how do I find that K value, that rate constant? What I can graph is I can graph whatever my concentration is of my reactant over the time it took. And by doing that, I can find the slope of this line, and the negative slope is basically going to be my rate constant. And so it's just like it was in algebra class, right? You just do, your rise over run, your y equals mx plus b kind of stuff to get what your k value would be just by picking two random points on the line and then just finding what the difference is between them on the y and then on the x. So here's what that rate law would look like if I was writing a zeroth order reaction for this specific example. So the rate would equal k, which I could find if I was graphing it. But in our situation, it rarely will ask you to do that. But I would put the concentration of N2O to the 0 power so that I know it is a zeroth order reaction. Now, what about first order reactions? So take a look at the data here and see how it's changed a little bit and how it's a little bit different. So let's say I have dinitrogen pentoxide, and it's breaking apart into nitrogen dioxide and also oxygen gas. So this reaction has a whole different rate to it. And notice that the rate is changing. So if I have 0.45 moles per liter of this, and then I double it, notice what happens to the rate. The rate doubles, right? So 2.7 times 2 is 5.4. And so the rate law is doubling. So in a first order reaction, if I double the reactant, that means I'm going to double the rate law. So this rate is going to actually change. Now, again, what about the K, right? So in this situation, if you were to graph the concentration over time, you would not get the rate constant. You'd have to actually take the natural logarithm of N2O5, which again is basically the inverse of the E value, like E being the constant. So again, probably a button you've rarely, if ever, used on your calculator, but the natural log of whatever this says over, again, still time. If I do that, the K would be equal again to the negative slope. So that means that all I would have to do is take this value, make it negative, and now all of a sudden, or if it was negative already, make it positive. And now I've got my rate constant for this situation. Now, once again, the rate law for this would be K times the concentration of my reactant to the first power. Notice, again, a lot of times people would say, oh, in an equilibrium expression, remember, I would have my products over my reactants, and then I would probably put a square here. I would have to square this and put it over these other things raised to their powers. Remember, don't mix up equilibrium expressions with rate laws. They're two completely different things. And so this is the way I would write my rate law for this first order reaction. Last type, second order reactions. Okay, so I've got two nitrogen dioxide molecules, and then I'm making two nitrogen monoxide molecules, and I'm making an oxygen molecule. Again, notice our rates here, and see if you can figure out what happens when we double or do something, let's say, to these rates. So hopefully what you can see is that if I am doubling something, right? So let's say I'm going from 0.0050 to 0.010. 1.35 times 4 is 5.40. So what that means is that when I double a concentration, I'm actually quadrupling the rate law. So I'm quadrupling that rate. So again, how would I figure out like the rate constant if I wanted to? Instead of using, just the value of NO2 concentration or using the natural logarithm, which is probably the hardest one, right? I just do 1 over this. So I do the inverse of whatever these are, just 1 over these amounts. And if I graph that against time, I get the slope immediately. Don't even have to change the negative sign or anything. It's always going to give you the slope because it's positive. So it's always going to give you that value if I graph it over time. Now, again, like I said, the balanced equation, it's purely serendipitous if you get the exact same value as this coefficient. And it just so happens the rate would be equal to K times the NO2 concentration squared. And it just so happens that if you were balancing this, you would put a 2 here. But again, it's purely coincidental that these are the same. All right, let's see a couple of examples. So it says, use the data that I have here to find the overall order of the reaction. Now remember, overall order means that I'm going to have to look at, okay, what order is, the reactant, the rate law with respect to A? What is the order with respect to B? And then I add them together in order to get my overall order of the reaction. So take a look here. I have 0.04 moles per liter of A, 0.04 moles per liter B. So this is kind of like your standard control. Now notice if I double the amount of B, what happens to my amount? It looks like it doubles. So that means B is going to be first order. Now let's do the same thing again, right? Now let's take a look at this experiment and this experiment. Let's compare them to each other. And so again, if I'm looking at this as my control, if I compare to this looks like I'm doubling the amount of A going from experiment 2 to experiment 3. And look what happens. 4.4 times 2 is 8.8. That means it's also first order with respect to A. So the rate law would look something like this. The rate would be equal to K times A to the first times B to the first. And that's how I would write that. Now, again, it's asking me, what is the overall order? That means that I take my N, I take my M, I add them together. That means the entire rate law is actually second order overall. Okay. So one more example. This one's a lot more complicated looking. We have 3 reactants, okay? And again, notice we have 0.35, 0.35, 0.35. So this is a good place to kind of look at like more of like a control. But take a look at our different values here. So I'm going to need to compare, and this one's a little bit harder to do, but let's try to make some sense here. So I want to get what, let's say, A is. So by looking at experiment 2 and experiment 1, that gives me a good relationship which I can use to compare these two values to each other. So going from here to here, what's happening to my initial rate to get from 8 times 10 to the negative 4 to get to 3.2 times 10 to the negative third. So again, it's looking like I'm quadrupling this. In order to get from here to here, I would have to quadruple that amount. Okay, now let's look at B. So B is right here. Let's see if we can find what we would need to compare them to in order to get B. So again, if I'm looking at 2 and 3, so if I'm comparing 2 to 3, it looks like, again, these are all the same, these are the same, but this is the only one that's changing. To double it, I'm going from 3.2 to 6.4. That's a doubling. And so since I'm doubling the reactants, and then I'm doubling my reactant, and then I'm doubling my initial rate as a result of changing that, that means that's going to be first order with regards to B. Now let's see if we can find C. So C, it looks like I would have to compare. So this is the only one that doubles. And then I would have to compare it to this one because I want A to be 0.7, 0.7, 0.35, 0.35. Notice the rate is the same, 3.2 and 3.2. That means it's 0 order with regards to C. So I would write it like this. I have a second order A, first order B, 0th order C, and it's asking me to find the overall order of the reaction. So that would mean 2 plus 1 plus 0, third order overall. But again, that's just one of the ways that we would use in order to figure out the overall order of reaction. If you have any questions, please let me know.